I'll share some chemical ideas, meditations. So yeah, I ran that facility, the geology department on this campus, and the keyword, I mean, so we use inorganic mass spectrometry, and the keyword is plasma, basically argon plasma, to break down and ionize molecules to be analyzed in a mass spectrometer. We run dust and many other things. These are more or less 6 end members that I could think of. We have run many thousands of each one, with the exception of forensics, which could be maybe 1,000, 2,000. Yeah, so we go from tissues to organics like crude oil or, archaeological bones. So we provide about 5 to 10,000 numbers a month. And by seeing so many types of samples, there is a lot of cross-fertilization in what you learn. There's no doubt about that. And dust is sort of special. I think it's more or less in the middle because it has a little bit of everything. So chemically speaking, or analytically speaking better, I would say that this model makes sense to me. So we have 3 components. We can think of 3 components: a detrital related to the geological time, like silicate minerals, where some elements that are very typical from that are zirconium, rare earth. We have autogenic. Some of the minerals are really autogenic and formed in the atmosphere. Some of them maybe represent autogenic processes in soils. These are typical elements that are related to that pool, and they represent probably a more recent time. And then we have what we call the carbon-rich component. All of it, I mean, from biology to soot to plastics, microplastic, etc. So ideally, the elemental and isotopic composition of these phases would be a good tool to identify sources and study the interactions with water, biology, and life, and soil. But the challenge is that this is a continuum. Of course, it's very hard to separate. And so what do we do? So that is what I'm going to talk about that. So the canonical methods for analysis are, let me say first that because mineral dust is a big bully, we normally eliminate the carbon phase. The component is gone. What happens with those elements? They are redistributed in a way that is, in my opinion, is not very well understood. And so I'm not going to talk about that. So I'm going to say, okay, so we assume the carbon is eliminated and we remain with some mineral phases, and we can either do a total digestion, basically dissolve everything, or just do some special leachings to target maybe nutrients or toxic elements. The normal ways of doing total is acid digestions or alkaline fusion. And I can talk about more about that, but if we have time. So soft leaching, there is a lot of possibilities, and sometimes people use a sequence that is not always the same order. So there are, water, we can define a soluble fraction, exchangeables. You need to remove absorbed ions, and that's ammonium is a typical way of doing that. Bioavailable, for instance, synthetic lung fluid, carbonates, from, very fine carbonates to maybe detrital calcite and dolomite. So there's a range of pHs where you can target that. Amorphous oxides, nitric acid, crystalline oxides, reducing solutions like targeting manganese. So there's a whole battery of things to do soft leachings in dust, soil, and sediments. Sediments is probably the easiest to understand because the water has some unifying role in the chemistry. But dust is special because you normally have a little bit of it, and it's sometimes supported on a filter, which makes things different. As I said, so total digestion is pretty straightforward. You can just run a reference material. There's many, not one specific for gas, but there are many soils and sediments. You can test your method. You can measure your recoveries, and you run a chemical blank, and you're done. I mean, there's not much to do. For leaching, so this is an example. This is not sequential. This is an AV horizon from southern Utah that has been treated with different solutions at different pHs, okay? So if you are interested in calcium as a nutrient available to roots, then you only have 0.5% in this case. But if you look at already pH 6, things really plateau very quickly. So you can basically, with a little bit of acid, get a lot of it. This is a carbonate-rich soil, okay? Iron has a very different behavior. So basically, these are logarithmic scales. So it goes for very little at pH 7 to about, I don't know, 1,300 or 3,000 probably. And these two behaviors are followed by many elements. So if you look at strontium or uranium, it will be like this because it's mostly in the carbonate. If you look at lead, for instance, it will be like this because it's associated with iron oxides, colloidal iron oxides. But there are things that are totally different. For instance, if you look at rubidium, it's a bad idea to try to remove rubidium if you have only protons, so you need ammonium. So you need ammonium, which is a big bully that is going to exchange with the clay surfaces and put it in solution versus an acid that is not going to do much of it. The problem with leaching is that the consistency is really poor. So this is an exercise run by the USGS on a reference material called San Joaquin soil, and two methods very related to each other, EPA 200.7 and 350B, were run. This is basically hot nitric acid, like 50% for some time. And you will see, I mean, it's hard to read, but the range that, I don't, like 28 labs participated, the range can be a factor of 5 or 10. So we're not talking 10, 20%. So this is the labs doing exactly the same thing, okay? So why is that happening? It's not totally clear, but we need to know that. I mean, so if we're going to compare results from different labs for leaching, you probably need to do something extra. So we tested several reference materials with different leaching at room temperature, different times, different temperatures, and different acid concentrations for some solutions. And it's very consistent. So probably, you know, heating is very difficult to do. I mean, depends on the size of the vessel that you use, the hot plate. I mean, so it probably, that inconsistency has to do with doing hot leaches which are targeting, these are methods that were created in the 90s for potential contamination of sediments. So you really need to take a lot out of them. But if you want to do something softer, you better, probably you are better working at room temperature, because a change of a few hours of a few degrees is still going to be within a 5% analytical consistency. Okay, conclusions for dust inorganic chemical analysis. So the total digestion has a very good consistency between labs, but it's not good for bioavailability or toxicity studies. So issues, of course, for dust, sample size, filter supported samples. So that is a problem. So filter supported samples can only be done, as far as I can see, using acids. There is no way of using the alkaline fusion method, which gives the better recoveries. Acids are still good. I mean, you are 90% on average. But again, so if you have 10 milligrams, easy. Half a milligram on a filter, you have to really work harder. So you check an SRM, a chemical blank, and you are done. If you want to do leaching, where I'll show you like a very ideal exercise using the same method is not consistent, but it's really useful for you. So sometimes you need it because you need to, you have bioavailability questions or toxicity questions. So again, sample size and filters, of course, are also a problem. Grinding effects, very hard to measure, but yeah, you grind and you get a different response. Organic matter treatment. Some people ash at 550 degrees to burn the carbon. Some people use hydrogen peroxide. So that can make a big difference too. And then it's element dependent. Don't do generalizations. I mean, if you're going to work on a broad spectrum of elements, yeah, you need to basically look at each of one individually. So ideally, you need to check some SRMs. There's not many for partial leaching, but some they start showing up. You have to do chemical blanks, of course, and probably check a temperature effect, the acid concentration effect, the time, and the stirring. So what isotopes can provide to this picture? Are they going to help to understand these complexities a little bit more? This is a high carbonate sediment from Lake Powell, and this is a low carbonate soil, that San Joaquin soil from California. When you measure the isotopes, the strontium isotopes are very much used to understand where the dust come from provenance studies. In this case, yeah, the scale is big and the error is really tiny. It's much smaller than the circle. But yeah, there is a small increase to more radiogenic values, but it's more or less the same. For this high carbonate soil, sediment, sorry, so you have more or less the same, like around 710, 0.710. And then when you do the total dissolution, then you jump to 725, okay? So in some cases, you see that the progression of incorporating more and more phases, chemical phases, has a big effect on the strontium isotopes, and sometimes it doesn't. And that's probably associated with the amount of carbonate. I'll show you one example that makes total sense. It's not the dust, unfortunate, but it's this Lake Powell sediment. So these are 10 sediments that were run under HCl, nitric, and acetic acid. So you remove the carbonate, but some oxide phases, but not much more, and then the total, okay? So all these three leaching are producing about the same value, okay? So and the average is about 7094. Lake Powell water is about that. So this is a carbonate that has been formed in the lake, basically, okay? So that is the unifying effect of the water that is basically creating that autogenic carbonate. Then the total, this would be maybe something that, if we think of dust, would be used as provenance, um, is very different from each other. Okay, that's good. So we want variability. But however, assuming that this is one member, and then this is the total, there is a second member that is associated with the detrital fraction. So you can calculate using this equation. It's like a 2N member model with a fraction for each and then a value for each. So we can call this one the detrital amount. The detrital amount is a black. And what you see immediately is that things that look different in the total look very similar in the detrital, or vice versa. Things that look similar in the total look different in the detrital. So obviously, for dust, this is never going to be such uniform. It's going to be more noisy. But chances are that we have two independent parameters for sourcing. So it's not only, the detrital fraction, but also maybe an independent autogenic fraction. Okay, I think that's all I have.